Good evening, friends. Now we are moving on to the second part of this three-phase connection numericals. In the part 1, three numericals of different types have been discussed. In this video lecture, which is part 2, 4 different numericals would be analyzed and discussed. So moving on to the first question of part 2, each phase of a delta connected load, which means the load given to us is of delta type. So let us draw a delta connected load. So this is how a delta connected load looks like, naming the terminals as R, Y and B. Now each load comprises of a 50 millihenry inductor in series with a, now mark this thing, there is a 50 millihenry inductor in series with a parallel combination. Now the load impedance for this given question is a combination circuit comprising of a series as well as of a parallel connection, and one has to be very careful while representing these type of elements in the circuit. Often students commit mistakes in these places. Instead of taking this in series with a parallel combination, at times they take the entire three elements in parallel combination. So these type of errors are to be avoided. So the question says that this inductor is in series with a parallel combination of a resistor and a capacitor. So this entire thing represents Z phase. The value of the inductor is already mentioned, which is 50 millihenry. The value of the resistor is given as 50 ohms and the value of the capacitor is given as 50 microfarad. It further states that the load is connected to a three-phase 550 volts. So what will be this value of 550 volts? As we have studied in our previous video lecture, that for a three-phase AC supply, the value of the voltage given in a three-phase supply question is always a line voltage unless otherwise specified. So 550 volts is the line voltage. Over here, 800 radians per second AC supply is mentioned, which means the value of omega is given to us instead of the frequency. Now the question says to figure out the 6 bits. Let us work out bit by bit. The first term says find out the power factor. Now one knows in order to find out the power factor, one must figure out the phi. The cosine of that angle phi will give us the power factor. Now this phi is the angle between V phase and I phase. This is a very important concept. Phi represents the angle between V phase and I phase. It should not be mistaken for the angle between VL and IL. It is absolutely incorrect. Now how can you figure out this angle phi? For a three-phase system, the angle phi can be captured in its load impedance, which is represented as Z phase. The angle which is present in this Z phase is the angle phi. And the concepts related to Z phase are being discussed in the earlier video. The link for the previous video is also provided in the description. So if I know the value of Z phase, then it will be easy for us to capture the value of phi. From there we can figure out cos phi. So let us start working with the value of Z phase. Now as Z phase is a series and a parallel combination of three elements, we have to figure out the value of Z phase first. I am drawing the load impedance once again over here for our reference. So this is the load impedance. It is given as plus JXL plus the parallel combination of R with minus JXC, where minus JXC represents the capacitive reactance of the capacitor. So upon further expansion, this can be written as, now before we should proceed ahead, one must know the values of XL and XC. Let us compute that first. What is XL? Omega L. Is the value of omega known to us? Yes, it is directly specified in the question and it's given as 800 radians per second multiplied with the value of L, which is given as 50 millihenry. This comes out to be 40 ohms. Likewise, Xc is given as 1 upon omega c. The value of omega is known to us and the value of C is given as 50 microfarad. So one has to multiply 10 raised to the power minus 6 and that comes out to be 25 ohms. So once we know the value of XL and XC, we can substitute these values in the Z phase expression and obtain the value of Z phase. Now one must remember that J is iota which has a value of 1 angle 90 degree and minus J has a value of 1 angle minus 90 degree. In case you are not aware of these values, upon direct substitution of these values into the scientific calculator will bear the same results. So the final value of Z phase comes out to be 22.36 angle 63.435 degrees ohms. Now what can we infer from this Z phase value? The angle has come out to be positive. As mentioned in our previous video lecture, if the angle of Z phase is positive, it implies the circuit is inductive in nature, which in turn means the cos phi would be of a lagging type. So the value of phi is already known to us. We know that the entire circuit is of inductive nature. So now we can figure out the value of the power factor. So phi has come out to be 63.435 degrees. It's a lag, or you can write it is inductive. There are two terms that you can use. You can either use the term lag or you can use the term inductive. Likewise, if the angle is of leading type, then use the term lead or capacitive. So cos phi will be cos of 63.435 degrees. That will come out to be 0.447 lagging. Now here is something that I would like to remind you once again. While taking the values of cos of this value into your scientific calculator, please check whether your scientific calculator is taking the values in degrees or in radians. For that, always try with sine 30 degrees. If the answer comes out to be 0.5, it implies that the calci is taking the inputs in degrees, else it would be taking in radians. For that case, you have to convert or change the mode from radians to degrees. So with this, we have computed the power factor of the total circuit. So the first bit is done. The second bit is asking us for the phase current. For the phase current, the expression is given as V phase upon Z phase. Is the value of V phase known to us? Not yet. We only know the value of VL, which was given as 550 volts. What type of circuit are we dealing with? Right now, we are dealing with a delta circuit. For a delta circuit, V phase is equal to VL, right in brackets delta. So it will have the same value, 550 upon Z phase. The value of Z phase is known to us, which is 22.36. Only the magnitudes are to be considered. VL, V phase, IL, I phase. For a three-phase system, do not compute these values with their angles involved. The angle should only be involved with Z phase. The reason being, VL and V phase have a phase difference of 30 degrees for a star connection, and IL and I phase have a phase difference of 30 degrees for a delta connection. In order to avoid these confusions while solving the numericals, for a three-phase systems, it is wise to consider only the magnitude part while solving the numericals, and all the angle part can be reflected in the Z phase, which in turn represents the load impedance per phase. So from here the I phase value comes out to be 24.597 amps. So with this, the second bit is also solved and we could figure out the value of I phase. The third bit asks for line current. Since this is a delta connection, I line and I phase are not same. Rather, IL is √3 times I phase. So upon substituting these values, one obtains 42.603 amps as the value of the line current. So with this, the third bit is solved. Now what are the rest of the bits says? It says to find out the power drawn, which in turn means the real power, which is represented by P. The next bit is asking us to find out the reactive power, which is represented by Q. And finally, kVA rating of the load, which is the apparent power. So one has to figure out the power values represented by P, Q, S respectively. So the expression of real power is given by, so there are two ways, but I'll be going with the first one. Upon substituting the values, the real power comes out to be 18.140 kilowatt. Moving on to the second bit, which is reactive power. The expressions for reactive power are given as, so there are three expressions. However, I will be going with the last one. The value of real power is known to us and we need to figure out tan of 63.435 degrees. So the reactive power comes out to be 36.3 kilowatt. Finally, coming to the apparent power. There are again three expressions for apparent power, which are root 3 VLIL, or 3 times of V phase I phase, or can be represented as P upon cos phi. I'll go with the last expression. P is given as 18.140 multiplied with 10 raised to the power 3 upon 0.447, which happens to be the power factor. So the apparent power comes out to be 40.5816 kilovolt amps. So this is how we figured out the different values of power. What was different in this question? The difference was in the type of the load that was given to us. The load was neither a series load nor a complete parallel load, rather it was a combination load. And for AC circuits, one has to be very careful with the calculations because that's a place where students commit more mistakes. So with this, we have completed our first question of this session. Let us move on to the second question. Now this is a different type of question. I won't say that this is a very important question, but yes, this is a different type of question and one has to even work out with these type of numericals. Let's see how this is different. A balanced star connected load is supplied. So it's a star connected load. Let me draw that first. Please make sure that you take out your terminals onto the right hand side. The reason was already being discussed in the previous lectures. So the terminals are named as RYB. It is supplied from a symmetrical. By symmetrical, it means it's a balanced 3-phase 400 volts. So line voltage is given as 400 volts. 50 Hz supply system. So the value of the frequency is given as 50. Now this is the important part of this question, or the part which is different. The current in each phase is 30 amps. Now what do we infer from here? The current in each phase is 30 amps. It means the phase current value is given to us, which is 30 amps. And that current lags 30 degree behind the phase voltage. I'm repeating that once again. That current, that means the phase current, lags 30 degree behind the phase voltage. So what we understand from this question is the value of the phase current is given to us and the angle by which the phase current lags or leads the phase voltage is also given to us. In this question, it is of a lagging nature. Lagging nature means the load must be inductive in nature. So it must be a series RL circuit. Quite possibly, let us see what is the question asking us to do. But here there is a very important note that one has to take care of. Since it is given in the question that the current lags 30 degree behind the phase voltage, one is not expected to write minus 30 degree with the phase voltage. I am repeating this again. Since it's given in the question that the phase current is lagging behind the phase voltage by 30 degree, one is not expected to write minus 30 degree with the I phase value. Why is it so? Because for a three-phase analysis, for the various parameters, that is the 4 parameters, we are not considering the value of angle associated with them. Rather, the values are associated only with Z phase. So, your objective is to associate this angle, this lagging angle with Z phase, rather than associating it with I phase. So, do not write it in this way. Rather, since it is a lagging circuit, it means Z phase will have certain magnitude and it will carry a positive angle of 30 degrees. Is that thing clear? Writing the angle with I phase is not wrong. Since the beginning, I have been telling you that for a three-phase circuit, we are not supposed to use the angle values with the 4 parameters, as it makes the analysis complex in nature. So at this stage also, one is not required to involve this angle value with any of the 4 parameters. Rather, one should make sure how to associate this angle value with the Z phase. So since this is a lagging type, what can one infer? That whatever will be the value of the phase impedance, it will carry a positive 30 degrees. Why is it positive? Because the angle positive with Z phase means it is a lagging type, or in other words, the circuit is inductive in nature. So this was the thing which was different in this question. Now let us move on with our first bit. The first bit says find out the phase voltage. Now this is a star connection. The value of VL is given to us. For a star connection, V phase is equal to VL upon root 3. So upon substituting these values, the V phase value comes out to be 230.94 volts. So with this, the first bit is done. Second bit says resistance and reactance per phase. Now we had concluded while reading the question itself that the current lags the phase voltage, which implies that the circuit is inductive in nature and probably it is a series RL circuit. Now, as the question in the second bit is asking you to figure out the resistance and reactance per phase, it simply implies that it is a series RL circuit. So, one is required to find out the resistance value and the reactance value. So, how would this load look like? The load per phase looks like this. This is R and this is L. Right now, the question is asking us to figure out the value of R and the value of XL. Because it says find out the reactance. It is not asking us to find out the inductance. So we must find out the value of R and the value of XL. Now these values of R and XL can be known only from the Z phase value. Unless the Z phase value is known to us, one cannot capture these values. So how to know these Z phase value? Z phase values can be figured out by V phase upon I phase expression. The value of V phase is known to us and the value of I phase is provided to us in the question. Upon substituting, it comes out to be 7.698 ohms. So now the magnitude of Z phase is known to us. Now just with the magnitude, one cannot capture the values of R and XL. The angle is important over here. Now here, the angle given to us in the question, let us move to the previous slide. The angle provided to us in the question comes into the picture. We already know that it is a lagging load and Z phase will carry a positive angle, that is positive 30 degree. Now the value is already known to us. So have we obtained the entire value of Z phase? Yes. So now we can capture the value of R and XL from this value. Now rewriting this Z phase along with its angle. Can we convert this polar form to rectangular form? Upon doing that, the values come out to be 6.67 plus J times 3.849. Now for a series RLC circuit, what is the expression of Z phase? It is written as R plus J XL. Have we obtained the same form as this one? Can we equate both these values? So this becomes the value of R and this becomes the value of XL. Now upon equating both these equations, we have obtained the value of R to be 6.67 ohms and XL to be 3.849 ohms. So this is how the value of the impedance elements can be found out when the phase current and its associated angle is provided to you in the question. So this is the important part of this question. So with this we have obtained the value of R and XL. The second bit is done. Now next it says find out the load inductance followed by the total power consumed. Now as I had mentioned over here, one is required to find out R and XL from the phase impedance values. However, to find out the inductance value, one has to first know the value of XL. Now the value of XL is known to us. At the same time, the value of frequency is also provided to us. So load inductance means it is the value of L per phase. This is what it means by load inductance per phase. Now XL has come out to be 3.849 ohms. This is equal to omega L, which in turn becomes equal to 2 pi FL. Now all these values are known. Can we find out the value of L, which is the load inductance per phase? So L will come out to be XL upon 2 pi F. The value of F is given out to be 50. So this gives the value of L as 0.01225 Henry or 12.25 millihenries. So this is how one has to figure out the value of inductance. Now we have already almost solved this numerical. Now one can think of the different aspect of this numerical. Instead of the lagging angle, if the leading angle is given to us, then it would imply a series RC circuit. And from there we can figure out the value of R and the capacitive reactance. And what would be the load capacitance? It would be the value of C obtained per phase. One can obviously solve if the question is of this type as well. I hope this part is clear. Now let us move on to the last bit of the question. One is required to find out the total power consumed, which is given as root 3 VL IL cos phi. Substitute the values known to us. Okay. Now most of the time I have a habit of using this expression. Now have we computed the value of IL in this numerical? No. So can I use this expression? Of course I can use this expression if I figure out the value of IL. But why do the computation? There is another expression for it, and that has to be used over here, which is 3 times V phase I phase cos phi. All these values are known to us. So let us substitute this expression for real power consumption for this numerical and not this expression. So 3 multiplied with 230.94, 30 is the phase current and cos phi is cos of 30. That will come out to be 17.999 kilowatts, which is nearly equal to 18 kilowatts. So these are the various ways in which you can solve the 3-phase numerical questions. With this, we have solved 5 questions, 3 in our previous video lecture and 2 for the present lecture. Now we have 2 more questions left, and I would say that the last 2 questions are really very important from the conceptual point of view. Let us see how they are. So this is the second last question. It is of course a very important question. 3 similar choke coils. What do you mean by choke coils? Choke coils means it's a series RL circuit. A resistor in series with an inductor. They are connected in star. So draw the star connection. If the line current is 15 amps, line current is a current which flows from the source side and finally eventually it reaches the load side. So for a star connection, IL is equal to I phase. The value of IL is provided to us. The total power consumed is 11 kilowatts. By power it means root 3 VL IL cos phi or 3 V phase I phase cos phi. That value is given as 11 kilowatts. The volt amperes is given as 15 kilovolt ampere. S has got 3 expressions. I am writing them all. And the value of S is given as 15 kilovolt amperes. Now these 3 values are known to us, and the values that have been asked to figure out are the line and the phase voltages, the VAR input. By VAR input it means the reactive power Q, and resistance and reactance of the coil, that is the element values of the load impedance. Now let us start with the first bit. The first bit says find out the line and phase voltages. Out of these 2 values, none are given in this question, and that makes the question important. Usually the voltage values along with their frequency is normally mentioned, and the voltage values mentioned in the question is the line voltage. So once the line voltage is known, the phase voltage is very easy to compute for a star connection or for a delta connection. But for this question, they're asking us to figure out the value of the line voltage and the phase voltage. So we must figure out either of this voltage first. Now the voltage values are available in the real power expression or in the apparent power expression. Now, which expression can we use? Let us assume I'm going with this real power expression and I'll go with this expression. The value of IL is known, the value of cos phi is not known. So I cannot use this expression. Coming to the second expression of real power. Since the value of IL is known, I phase is also known because this is a star connection. But I do not know what is cos phi. So I cannot figure out what is phase voltage. Now coming to the apparent power expression, let us start with the first one. The value of IL is known and there is only one unknown value available over here, and which is the line voltage. And the value of S is already given to us. From this expression, one can find out the line voltage. So let us do that. S is given as root 3 VL IL. So from there VL comes out to be S upon root 3 IL. Please make sure that S is in kilovolt amperes, so do not forget to multiply 10 raised to the power 3. So with this the value of VL comes out to be 577.35 volts. So now the value of VL is known to us. If the value of VL is known to us, one can figure out the value of V phase. V phase for a star connection is given as VL upon root 3. Upon substituting the value of VL in the V phase expression, the value comes out to be 333.33 volts. So I am writing the obtained values over here. We obtained the value of VL, which is 577.35 volts, and V phase came out to be 333.33 volts. So the first bit is solved and we have obtained both the values. Now the second question asks us about the VAR input. VAR is the reactive power. There are three expressions for reactive power. Let me write down that first. So these are the three sets of expressions using which the reactive power can be computed. And in all the numericals I have used this expression. However, currently for this numerical I am not aware of this value of phi. Why is it so? Because to us only three values are given. One is IL, one is value of P, one is value of S. Now, the value of phi can be obtained only from this phase power value or from the S value. Now, let me go to the previous slide. Right now, if I use this power expression root 3 times VL IL cos phi, I can get the value of cos phi. Why is it so? Because the value of VL is already known to us. IL is known to us, the cos phi can be readily obtained. Likewise, if I use this expression also, I can obtain cos phi. However, I am not going to use either of these expressions. Rather, I am going to go for this expression. Because for this, the value of S is known, the value of P is known. So one can directly obtain the value of cos phi. One must not come under this impression that using these expressions, one will not get the values of cos phi. It is not like that. You will obtain the value of cos phi no matter whichever expression you are going for. But since this expression is quite handy, and I would definitely ask all the students to go for these expressions that are obtained using the power and the impedance triangles. Because sometimes one or the other values are not known to us. So directly by substituting the formulae, one may not find out the answer. So the expressions that are obtained from the triangle values, from the power triangle or from the impedance triangle, they help us a lot. So I am going for this expression. So what can I write? S is equal to P upon cos phi. So cos phi would come out to be P upon S. P is given to be 11 kilowatts and S is given to be as 15 kilovolt amperes. So that gives the value of cos phi as 0.7333. And what is the nature of this cos phi? Is it leading or lagging? Now let us go back to the question to figure out this thing. What does this question says? It says 3 similar choke coils. Coils means it is inductive in nature. Inductive means it is of lagging type. So this is lagging in nature. So once the cos phi value is known to us, can we figure out the value of Q? Yes. Using this P tan phi expression, one can obtain, or you can go for any either of these expressions. For that, one has to figure out the value of phi first. That will come out to be cos inverse of 0.73, which is 42.836 degrees lag. So with this, Q comes out to be P tan phi, which is 11 multiplied with 10 raised to the power 3 tan of 42.836. That comes out to be 10.198 kilovar. So this is the var input asked to us. So the second bit is also solved. The third bit is asking us to figure out the resistance and reactance value. The approach will be same that we had done for the previous question. We require the Z phase value followed by the angle, that is the angle phi between the V phase and I phase, which will be carried by Z phase. So how to obtain the value of Z phase? Z phase is given as V phase upon I phase. The value of V phase obtained by us is 333.33 volts upon the value of I phase is 15 amps. Why is the value of I phase is 15 amps? I phase is equal to IL. The value of IL is already provided. This is a star connection. So these two parameters are equal. So Z phase comes out to be 22.222 ohms. What is the value of phi? It is 42.836 degrees. Now this is of lagging type. Since this is of lagging type, it will appear as positive with the Z. So Z phase will be written as 22.222 angle positive 42.836. Now expand this polar form into the rectangular form. It comes out to be 16.295 plus J times 15.109 ohms. So they are in the same form as R plus J XL. So equating both the sides, this is the value of R and this is the value of XL. So with this we have solved the third bit as well. So this comes to the end of this question. Now let us not end this question over here. Let us extend this question, as this question was a bit different. In the previous video lecture, we had studied about the same load impedances connected in a different structure. In this question, the impedances were connected in star. Now let us assume that these impedances are now connected in delta. And one is required to find out the current values, the real power and the reactive power. I am writing down the question in a new slide. We will go with the same question. We are actually going with a continuation of this question. Now our extended question is, the same loads are being connected in delta. So we need to figure out the values of certain parameters. So I have noted the extension part of the question. Now these same coils are now connected in delta to the same supply. We are not changing the supply. So one is required to find out I phase, IL, P and Q. So in our previous video lecture, we had discussed an important aspect. If the load impedances are same and the structures are changed, what does one mean by these structures getting changed? Either from star to delta or from delta to star. So there are only two parameters which will remain same. One is the line voltage, the other one is the load impedance per phase. Apart from these two parameters, none of the values will remain same for this set of condition. What is the reason? Upon changing the structure, the powers do get changed. By power, one refers to P, Q and S. So if these values change with a change in structure, that is with a change in delta to star or star to delta, the parameters like IL, I phase, V phase, they cannot remain same. They have to eventually change. So For a given question, when the load impedances are kept same and their structures are being changed from star to delta or vice versa, in that case, there will be only two parameters which will remain same. One is the line voltage, another one is the phase impedance of the load. So for this question also, the loads or the coils are now connected in delta. Now based on this new connection, one has to figure out all these values. So one must not come under this impression that these values were already figured out there. So we will just use those values. And in fact, for this question, the values of IL is given to us, P is given to us, S is given to us. Do not use the value of IL, which is given as 15 amps, straight away for a delta connection as 15 amps. You cannot do that. The only two values that we can use it from our above analysis are the values of VL and the Z phase. Because the moment the connections are changed with the same load impedances, none of the values would remain same. They will change. So what was the value of VL obtained? So these are the values of VL and Z phase that we had obtained earlier. VL had come out to be 577.35 volts and Z phase is 22.222 angle 42.836 degrees. Since the Z phase remains same, it implies that its magnitude and the angle both will remain intact for any type of connection change. So in order to find out I phase, the first bit says to find out I phase. In order to find out I phase, one must figure out what is the value of V phase. Now this is a delta connection. So draw a delta connection for the reference. For a delta connection, VL is equal to V phase. So what will be the value of V phase? It is 577.35 volts. Now could you see the difference over here? When these coils were connected in star, the value of V phase was not 577. Rather, it had come out to be 333.33 volts. But now, the same load impedances are connected in delta. So, these line voltage would be equal to the phase voltage. Now, since this phase voltage has got changed, naturally, this phase current will also change. So, what will be the value of this phase current? Phase current is given as the phase voltage upon the load impedance per phase, which is 577.35 upon 22.222, which comes out to be 25.98 amps. With this, we have solved the first bit. Now finding out the second bit, which is IL. Whenever a question is being asked to you, draw that particular connection and write down the relationship between the line parameters and the phase parameters. Since this is a delta connection, line voltage is equal to phase voltage and the line current is equal to √3 times of the phase current. The phase current obtained in the previous slide has come out to be 25.98 amps. So IL will be √3 times of this value, which is 45 amps. Now can you see one thing? For a star connection, the IL was given as 15 amps in the question itself. However, for a delta connection, it came out to be 45 amps and not 15 amps. So this would have been the mistake had you taken the value of IL which was already given in the question. So these small things one has to take care of. The moment the connection changes, only two parameters shall remain the same, and they are VL and Z phase. Rest any parameter that comes into the picture, whether it is IL, I phase, V phase, all type of powers, they are bound to change. So with this we have obtained the second bit as well. Now the third and the fourth bit asks for finding out the real power and the reactive power. In the previous slide, we had studied a relationship between the powers obtained for a delta connection and the powers obtained for a star connection. And the relationship says that the power for a delta is always 3 times the power for a star. Now in this question also, we have already obtained the value of Q in the previous part of the question. So Q had come out to be 10.198 kilovar. Now Now in this section, this is a delta connection. You can directly multiply 3 with the previous value. And that will come out to be 30.594. This is var. The unit of Q is in var. 30.594 kilovar. In case you have forgotten this expression, you can use the normal expression, which is Q is equal to P tan phi. So let us now figure out P for this expression. P will be root 3 times VL IL cos phi. So root 3 times 577.35, IL is 45 and cos phi is 0.7333. So P will come out to be 32.998 kilowatts. Using this value of P in this expression, the value of Q will come out to be 30.595 kilovar. So this is how you can obtain the power values for the change in connection from star to delta. And you can see both the values are same. So this is the third question solved for this session. Now let us move on to the final question, and the final question is a very important question. Remember, while studying about the star and the delta connection, we discussed about the source and the load connections. And I had specifically told you, unless the connection of the source is being asked in the question, one is supposed to be not bothered with the source part as well. So this last question that we will be discussing right now has a source connection involved. So let us see how we will solve a numerical having a source connection type specified as well as a load connection type specified. So this is the last question that we are going to discuss. This is a very important question. It says there is a 3-phase star connected source. Look here, it says a source feeds 1500 kilowatts at 0.85 power factor lag to a balanced mesh connected load. Now this is the source. The source is a star type and the load is a mesh type. So both the connections of source as well as load are specified in this question. So one is required to draw both the connections of source and load in this way. Now as you can see, the left hand side represents the source and this represents the load. Now we need to connect the terminals of red to red, Y, that is yellow to yellow, blue to blue. Let us do the connection part. The red part is connected to red. This is the Y part, so it's connected to Y, and this is the blue part. So source red part, that is source subscript R, is connected to the load subscript R. Source subscript yellow is connected to load subscript yellow. Source subscript blue is connected to load subscript blue. So we have represented the complete set of source and load connection. Now let us see what is the question asking us to do. This source is feeding a power of 1500 kilowatts to this load. So power is 1500 kilowatts. At the same time, the power factor is specified, which is cos phi, which comes out to be 0.85, and it's mentioned it is lag. What can we infer from this lag? Lag means the circuit is a RL type and it is inductive in nature. The question is asking us to figure out the value of the current, its active and reactive components in each phase of the source and the load. Now if you read this question carefully, the question is asking us to figure out the current. Where is it asking us to find out the line current or the phase current? It is asking us to find out the phase current because it says in each phase. At the same time, it is asking us to find out its active and reactive components. Whose active and reactive component? The phase current active and reactive component. What do you mean by that? What do you mean by the active component? By active component, one means the component which actually does the work. See, for example, we have discussed over here the real power. The real power is the power where the real work is done, the work which is visible to all, which is given by the expression root 3 VLIL cos phi. Whereas reactive power is the power which delivers a work which is not visible to us, it is not in real, and it is represented by a component of sin phi, and real power is given by a component of cos phi. So in this question, it is asking us to find out first the phase current and then its active component, which means the component which is actually working towards the active presence of the work done, which is I phase cos phi. We can also write this power expression in another manner, 3 V phase I phase cos phi. So this I phase cos phi is the active component of the phase current, whereas 3 V phase I phase sin phi, this I phase sin phi is the reactive component of the phase current. So question is asking us to figure out these three values for the source side as well as for the load side. Now for the load side, where will the phase current flow? Over here. And for the source side, where will the phase current flow? Over here. So one has to find out the phase current for both the sides first, and then figure out the active and the reactive components. And lastly, the question says the line voltage is given as 2.2 volts. This has to be kilovolts. 2.2 volts is a very small value. It is kilovolts. So I am writing the value over here. VL is given out to be 2.2 kilovolts. Now with this, one has to start with the workout. Now there are two aspects to this numerical. One is the source side, one is the load side. So far we have solved 6 questions, and for all the questions we were always computing the load part first. So let us now begin with the load part first, followed by the source part. I am drawing the source and load connection once again over here. The load is connected in delta. Now the value of VL is known to us. If the value of VL is known to us, it means it is common to both the ends. So VL is given as 2.2 kilovolts. From here, can we figure out V phase? Yes. V phase will be equal to VL since it's a delta connection, which will come out to be 2.2 kilovolts. Now, in order to find out this I phase, one requires the value of Z phase. In this question, nothing is mentioned about the load parameters. However, we have been provided with a vital piece of information, that is, the source is delivering the load a power of 1500 kilowatts. This power is actually delivered at the load end, and it is delivered by the source and it is coming towards the load. Now this is a very important point. This power is delivered by the source and it is coming to the load. In the previous question, whatever we have discussed, the load was only changing the structure. It was either becoming star or it was becoming delta. So the power value here and here were not same. Over here, this is not the case. Here we have got a source, we have got a load. So this power is being delivered by this source to this load, which means both the sides are carrying same amount of active power. I am repeating the part once again. In this question, the source connection is specified to us and the load connection is specified to us. And it says the source is delivering a power of 1500 kilowatts to the load. So the source is delivering this power and the load is also taking this power. Do not get confused that since the source is in star connection and the load is in delta connection, these power will get changed. No. Why is it so? Because in the previous questions, it was only the load structure which was changing. The load was earlier in delta or in star and it was getting converted to star or delta. It was always this right hand part which was changing. The source was delivering that amount of power, but since the right hand part was changing, so the power taken up by the two different types of connections won't remain the same. If under the star connection, the power is 1 kilowatt, for a delta connection, the power would come out to be 3 kilowatt because it is the same load impedance which is changing the structure. In this case, it is the source which is delivering the load and none are changing the structure. Source is delivering this power and the load is taking this power. So this power remains intact. I hope this part is clear to you. In this numerical, this is a very, very important part. In all the previous questions, the load was changing its structure. The load was changing from star to delta or from delta to star. Hence, the power of the circuit on the load end was changing. But in this question, the source is delivering a power to the load. So, irrespective of any connections, whether it is a star or a delta, whatever power is being delivered by the source has to be taken up by the load and there will be no change of power on either end. I hope I have made myself clear. So what is the expression of this power? We are still on the load side, so we will be discussing with the load's perspective. It is given as root 3 VL IL cos phi. The value of VL is known to us. The value of cos phi is already given to us. So one can figure out the value of IL. So P is equal to root 3 VL IL cos phi. So IL will come out to be P upon root 3 VL cos phi. Upon substituting all these values, I am substituting over here. So the value of IL will come out to be 463.12 amps. Now once the value of IL is known, can one figure out the value of I phase? The load is delta connected, so the relationship between IL and I phase is IL is root 3 times of I phase. So I phase will be IL upon root 3. I phase comes out to be 267.38 amps. So with this, we have solved the first bit, which is computing the I phase for the load side. Once we know the I phase, we can figure out the active and reactive components just by multiplying cos phi and sin phi. The value of cos phi is already given as 0.85 lag. So I phase cos phi will be 267.38 multiplied with 0.85 and it comes out to be 227.27 amps. Likewise, the reactive component of the phase current at the load side can be given as I phase sin phi. One has to figure out the value of sin phi, which is sin 31.788 degrees. This is the value of phi obtained by cos inverse of 0.85. So that gives a value of 140.847 amps. So with this, we have figured out the phase current, the active component of the phase current and the reactive component of the phase current at the load side. Now let us start working at the source end. I am drawing the source and the load representation once again. This is the source and this is the load. And the value of VL is known to us. So I'm writing it here, VL is 2.2 kilovolts. Now what does the question says? The question says to find out the I phase, the active component of the phase current, the reactive component of the phase current at the source end. That is on this side. In order to figure out the phase current value, I require the load value along with this VL value or some other value, because just with this voltage value I won't be able to figure out the I phase value. Now what is the another important thing that was given to us in the question? That was the power value, which had been presented as 1500 kilowatts. What did I mention in the previous slide? In this question, the source is delivering 1500 kilowatts to the load. So whatever power is delivered by the source is being taken up by the load. There is no change in power. In the previous questions, there was a change in power because the load was changing its structure. In this question, the load is not changing the structure, the source is delivering and the load is taking that. So the second condition known to us from the source end is the power delivered is 1500 kilowatt along with a power factor of 0.85 lag. So for this question, whatever conditions were used for the load side, the same conditions are to be used for the source side as well. So based on these conditions, we have to figure out at least the line or the phase value of the current. So P is given as √3 times of VL IL cos phi. The IL will come out to be the same that we have obtained for the load, which had come out to be 463.12 amps. So in this question, we are seeing that the set of conditions that we used for the load side is remaining same for the source side as well. In fact, the set of conditions always remain same for the load side as well as for the source side. The set of conditions only change when the load side connections are being changed. And so far in all previous 6 questions, we might have dealt with the change in the connection type at the load end. Hence, the set of conditions do change. So with this, we have figured out the IL at the source side. It will be equal to IL because the source is a star connection. So this is the phase current at the source side. Once the phase current is known, one is required to find out the active component of the phase current at the source side. Now since the set of conditions are going to remain same for both, the cos phi is already known to us as 0.85. So it will come out to be 393.652 amps. Finally, coming to the reactive component of the phase current, it will be given as this. So with this, we could figure out the phase current, the active component as well as the reactive component of the phase current at the source side. There is one thing that I need to tell you at this point of time, that we obtained this reactive component of the phase current using this expression. But remember how we used to obtain the reactive power? The reactive power can be obtained by P tan phi. The same thing can be used over here. This I phase sin phi, which is the reactive component of the phase current, can be written as the active component of the phase current multiplied with tan 31.788. So what I'm trying to say over here is any reactive component of any parameter can be obtained by multiplying its active component and the tangent of the angle. between the voltage and the current. So with this, we come to the end of all the 7 questions. We have discussed a lot of important concepts. Those are very, very important. I'm repeating the 2 important concepts here once again. If a load is in star connection and it is getting changed to a delta connection, there are only 2 sets of parameters which will remain same, that is VL and Z phase. But if there is a combination of source and load and none are changing their connection, like we solved in the previous question, source is of star type and load is of delta type. In that case, same sets of conditions are valid on both the ends. So this is a very, very important difference one has to take care of while solving the numericals. So these were some of the important numericals on 3-phase AC systems. I hope you have understood. If you have any doubts or any queries, please do let me know. That's all for this video lecture. Thank you for watching.